Hello. The title of this presentation is the Measurement Problem 1, Wave-Particle Duality in Schrödinger's Cat. This is our first video out of 7 in the Quantum Measurement Problem video series, which is designed to supplement our book, The Quantum Measurement Problem. I'm Dr. Michael Steiner, and I work with Dr. Ronald Rendell on the investigation of the measurement problem. Stop that, Schrödinger. Bad Schrödinger. The measurement problem is the problem to explain how wave behavior is consistent with particle behavior when a measurement occurs. To understand the measurement problem, we will need to explain various concepts in detail. There are a number of books, videos, etc. on the measurement problem. Some are very good, however, few go into substantial detail. The devil, however, is in the details. The measurement problem has many details that are often left out in its explanation. However, it is essential that one understand these details in order to fully comprehend the problem. One can't be expected to solve a problem one doesn't fully comprehend. In order to better understand the measurement problem, we have both written a book and produced this video series. These videos are designed to complement our book, The Quantum Measurement Problem. By both reading the book and watching these videos, we hope to create an interesting, enjoyable, and entertaining way to learn what arguably could very well be the most important of all scientific problems. In this, our first lecture, we will concentrate on wave-particle duality, interference in Born's law, Schrödinger's cat, and the measurement problem. After finishing this video, we'll go on to video 2, characteristics of unitary evolution. In the second video, you will understand the relationship of the measurement problem to the issues of reversibility and irreversibility, and as well entropy change. You'll also learn to understand unitary interactions related to measurement. This background in unitary evolution is a necessary prerequisite in order to begin our third lecture, which will be in 2 parts, and which is perhaps the most important, in that we will pull together the material of the first 2 lectures in order to show why, subject to assumptions, that the measurement problem implies that a real non-unitary process exists. This will allow you to more fully appreciate the significance of this problem. In our 4th lecture, we will discern correct approaches from incorrect approaches. In our 5th, we will discuss from a historical perspective the measurement problem and examine what can one learn from history. In our 6th video, Scientific Approach, the importance of the scientific approach will be discussed in terms of inductive versus deductive reasoning. And in our 7th and final video, we will present on closed and open system approaches, where you will learn the basics of the closed and open system approaches to resolving the measurement problem. Now, let us turn our attention to wave-particle duality. Wave-particle duality is the concept that a single quanta has dual wave and particle properties. The wave function psi is a mathematical representation of this wave, which evolves according to Schrödinger's equation until it is measured. Once a wave is measured, it exhibits particle qualities. In order to examine the wave properties of light, we will consider the double slit experiment. Here we have a light source represented by the flashlight that shines on 2 hollow slits for which light can pass through. Here the light source has been turned on, and it can be seen emitting a light beam, which we represent as a sinusoid or a wave. And this wave is impinging on the double slit. Here we examine the rear or the output of the slits, and let us consider the possibility that from each slit there is only a single wave emitted as shown. Actually, this is not correct, and in fact one needs to consider that there are multiple paths possible from each slit. That is, there are actually 2 paths that are possible to any given point coming from either slit. Because of the possibility of 2 different distinct paths to the point A, one coming from the left slit and one coming from the right slit, one must sum the waves over the contributions from both slits to determine the new wave at A. One must similarly sum the waves emitted from both slits to determine the new wave at B. Here we see the pattern that results from correctly summing over both paths. Nulls and peaks result due to the two-path interference. Let us summarize then the wave properties of light. When light is emitted, it travels as a wave, even for a single photon. Light passing through a double slit passes through both slits in a superposition. Interference results between the two paths. This results in an interference wave function that has nulls and peaks due to this interference. This can be experimentally confirmed by placing the detectors at different locations. It should be noted that the wave properties of emission obey unitary evolution and are completely reversible. This will be important when considering later the measurement problem. Now, everything would be quite easy to explain at this point if light continued as a wave. In fact, Maxwell's equations described light as a wave as early as 1861. But light was also hypothesized to be quantized in indivisible units called photons by Einstein, with energy equals h nu in 1905, which extended Planck's thermodynamic arguments regarding blackbody radiation in 1899. Interestingly, these two concepts had existed prior to both Maxwell and Einstein. Newton had proposed that light was corpuscular in 1675, while Huygens proposed that light was a wave as early as 1678. It may be noted that Newton's corpuscles were not quantized in the sense of Planck and Einstein. Let us now switch sides, and instead of considering the wave particles of light, consider the particle properties of light. When light is measured by a detector, it transfers an amount of energy, h nu, from the light to the matter. Once a single photon wave is measured by a detector, the photon wave function must cease to exist. Otherwise, an additional energy h nu could be transferred to other detectors. Let us consider once again the example where a light source emits a photon that impinges on a double slit. This produces interference. We see constructive interference in the red, where there are peaks, and we see destructive interference in the blue, where there are nulls. Now, under the wave property of light, one might expect that these waves would continue to go on and on and on. However, when one places detectors in the region, seen here as the blue detectors, one finds that only one detector will detect or go off. And these detectors are found to detect with probabilities that are related directly to the amount of constructive and destructive interference. Let us now consider what happens when one of the detectors actually clicks or detects the photon. In this example, shown here, we see that the detector on the left, which was initially blue, turns red, indicating that it has detected a photon. In this case, the photon wave function that we saw previously, the wave, ceases to exist. Energy equals h nu is transferred to this detector on the left. If one looks on the right detector, one will find that no energy is transferred to that detector. And now, we begin to see a wholly remarkable picture beginning to emerge. Wave-particle duality is a single quanta having both wave and particle properties. The photon appeared to act as a non-localized wave until it was measured, whereupon its localized particle properties are realized and energy is transferred to the localized detector. What we have been seeing can be further illustrated diagrammatically. On the left, we have our initial description for which a wave is emitted by the light source, and for which interference subsequently occurs via the many paths that are possible coming out of the two slits. Now, this wave picture evolves into one of two possible configurations that we show on the right. In the first possible configuration, at the top right, we see the left detector has gone off or detected the photon and absorbed the photon energy equals h nu, whilst the other detector remains blue. In the second possible configuration at the bottom right, we see that the right detector has gone off or detected the photon and it has absorbed the energy equals h nu, whilst the other detector remains blue. And so, what we have are two different possible descriptions. And these possible descriptions are represented by different probabilities for these two possible configurations corresponding to the two possible outcomes for the experiment. In 1926, Schrödinger found a wave equation in which Planck's constant h appears, which is now called Schrödinger's equation. It is obeyed by quantum waves for particles with mass m. In 1948, Feynman showed that Schrödinger's wave equation is equivalent to the summing over paths that we used in the double-slit examples. Photons actually have zero mass, but the summing over paths was shown to work for them as well. Now, before measurement, one is required in quantum mechanics to sum over all contributing wave functions to form coherent superpositions, such as the contributions coming from the two slits at a given point. This results in the interference that we've seen in the two-slit experiment. And if the wave simply continued on and on and on, we would simply continue, but what we have seen is that only one particular configuration of detectors out of many possible configurations actually occurs. And in order to describe that, it was Born and Born's rule that was introduced shortly after Schrödinger. One takes the wave function and squares it, and this eliminates further interference as the wave transfers its energy to only one of the many possible detectors. Let us now turn our attention of how to compute the probabilities in Born's rule in a more detailed manner. Let us denote the position of the detector to the left of the slit as x1 and the position of the detector to the right of the slit as x2. We'll denote as t0 the time that the detector goes off or detects the light. In order to compute the probability of the top left detector to go off, which is shown by the upper blue arrow that takes the wave configuration shown on the left to the diagram shown in the upper right, we'll take the wave function psi1, which is the contribution from the wave that went through slit 1, and evaluate it at x1 and t0, and we'll add to this the wave function psi2, which is the contribution from the wave that went through slit 2. And we'll also evaluate this at x1 and t0. This addition is coherent, so can exhibit both constructive and destructive interference. But we are not done. We now square this value, and it is this squared value that equals now the probability that this particular configuration occurs for which the left detector detects the photon. Now there is another possible configuration of detectors that can occur, and this is shown by the other blue arrow that takes the wave configuration on the left to the configuration on the bottom right, in which the right detector goes off or detects the light. To compute this case, we take the wave function psi1, which is again the contribution from the wave that went through the slit 1, and evaluate it at x2 and t0, and add to this the wave function psi2, which is the contribution from the wave that went through slit 2, and we also evaluate it at detector 2 x2 position and t0. Again, this addition is coherent, so it can exhibit both constructive and destructive interference. But again, we are not done. We now square this value, and it is this squared value that equals now the probability that this particular configuration of detectors occurs for which the left detector detects the photon. And you'll note that there is not always the left detector that goes off or the right detector that goes off, but there are two potential cases that can occur. So generally we call this non-deterministic propagation versus a deterministic scheme in which everything is determined in the evolution. And so there could only be one outcome for deterministic evolution, which one might expect would still be the wave that propagates in time. On the other hand, in the non-deterministic case, we have different possible experimental outcomes. We would like to re-emphasize several important points. One must sum the waves emitted from both slits to determine the new wave equation at A and B. Before measurement, one sums coherently the wave functions from both slits. However, detectors via Born's rule respond with probabilities via psi1 at x and t plus psi2 at x and t, the whole thing squared, which includes a non-coherent squaring process. Note that if one takes psi1 plus psi2 and squares it, this equals psi1 squared plus psi2 squared, plus an additional term, which is psi1 psi2 conjugate plus psi2 psi1 conjugate. And this additional term is an interference term. And this is distinctly different than what would be obtained if one were to take psi1 squared and add to it psi2 squared. Now, these two cases can be experimentally distinguished, and it is found that, in fact, one sees this extra interference term. And this confirms that light evolves coherently via Schrödinger's equation. In this way, one can experimentally isolate and verify processes that evolve unitarily. An important question examined in later videos is whether or not non-coherent processes can also be experimentally investigated. This is an important departure point for a more advanced understanding of the measurement problem. Now, from what has been presented so far, one might argue as to whether or not a probabilistic description is really needed. For example, perhaps each time an experiment is conducted, the detectors are in some slightly different initial state, and so this might explain deterministically why the different outcomes occur. In fact, Schrödinger himself desired that his equation be correct in all circumstances. This issue is critical to understand and will be addressed in the second and third video. Schrödinger's equation did not predict that the cat would either be alive or dead in these experiments, but instead would remain in a superposition of life and death. Niels Bohr tried to explain to Schrödinger that his equation could not be solely correct to describe nature. But Schrödinger stubbornly refused to accept this, and there is a legend that he nonetheless conducted experiments to see if this were really true. Unfortunately, as the legend goes, the experiments did not always go as planned, and towards the end, Schrödinger was known to hide underneath the table. Now, it is well known that the measurement problem is directly related to a number of philosophical issues. It may be noted that most philosophers completely reject the notion that Schrödinger ever performed such experiments. Now we are in the position to understand the basics of the measurement problem. The resolution of the measurement problem requires one explain how the predicted unitary Schrödinger evolution, or wave behavior, is consistent with the particle behavior when a measurement occurs and energy E equals h nu is transferred to a detector. This definition, however, is not sufficient to fully understand the measurement problem. In our upcoming second and third videos, we will greatly expand on the measurement problem, and you are highly encouraged to watch these videos if you really want to seriously understand this problem and its potential ramifications. To summarize, in the current video, we have presented on wave-particle duality, interference in Born's law, Schrödinger's cat, and we provided a basic definition of the measurement problem. This video is a companion to our book, The Quantum Measurement Problem, published by Inspire Institute and available at Amazon.com. This book is the first volume of a book series entitled Progress on the Physics of Quantum Measurement. Be sure to visit our website, which has more videos and additional information on the quantum measurement problem at theqmp.com. We also have been working a long time on our own approach to resolving the measurement problem that involves closed systems that function as measurement devices. The details of the approach can be seen at internon.com.